In this video, I'm going to talk about Laplace transforms. Laplace transforms is nothing but we are transferring a time domain or time dependent quantity into a time independent quantity, and then once it is time independent quantity, it is easy for us to solve. Once we solve it, again we'll convert it back into time domain. Okay, so far we did the same thing in the frequency domain. Why do we need Laplace transforms? The main reason behind it is, so far the circuits we solved are very small circuits. What if there are hundreds of elements, more capacitors, more inductors involved in that circuit? Then we'll end up having many number of equations. So Laplace transform is one of the way to solve those circuits. Okay, so the definition of Laplace transforms is it is an integral transformation of a function f of t from the time domain into complex frequency domain, giving f of s. So if you have f of t in time domain, we are converting that into f of s. Okay, so at the starting you will end up having a differential equation in time domain f of t. We're converting that into algebraic equation by using Laplace transformation. This L indicates Laplace transformation. So once you convert it into algebraic equation, we're going to represent that as x of s or f of s. It doesn't matter. I can represent f of s. Now in s domain, we're going to solve it. Once you solve it, whatever you have, x of s or f of s, let me you're going to end up having different value, different function, because maybe I'm looking for a current or voltage, current passing through any element, or voltage across any element, so it's going to be x of s. Let me now you're going to convert that back into, this symbol indicates inverse Laplace. We're converting back into x of t. Okay, this is simply Laplace transformation. In mathematics, you learned how to transform this. So Laplace transformation of f of t. In time domain, we always use small letters. When it comes to s domain, we always use capital letters. Okay, f of s equal to 0 to infinite f of t e to the power of minus st dt. This is the basic formula to transfer any function into s domain, where s equal to sigma plus j omega. Now we'll take a simple inductor. So if we look at an inductor, here is an inductor, say I of t is the current passing through it. Okay, so what is the voltage drop across the inductor? I'm going to take this as v of t equal to L times, if I take that L as the inductance value, v of t equal to L times dit by dt. That's the voltage drop across the inductor in time domain. Now if I use this transformation, and if I convert this into s domain, I'm going to call this as v of s L times this d by dt is going to be s times that I of t. I mean, in s domain I'm going to use the capital letters, s times I of L. Okay, I of L is the current passing through that inductor. Okay, so basically it is nothing but v of s is nothing but v of s is nothing but SL times I of volt. That's the voltage drop across the inductor. Now here I'm taking initial condition 0. So what is initial condition? I'm assuming this inductor is empty, it's not at all energized. Now if you have some energy initial, so with initial conditions, if I take it with initial conditions are nothing but this inductor has some initial energy stored in it. Okay, so with initial conditions, okay, I'm going to take this as I of t v of t plus or minus. So say there is some initial current I naught equal to I. So here VL is nothing but L times dit by dt. When I convert this into S domain, Vs equal to, or I would say, instead of, I'm saying S because of the S domain, probably it's a good idea to say VL of S or VL. Okay, I'm going to say VL. VL equal to L times Si minus I naught. So V of L equal to LSI minus Li naught. That's the voltage across the inductor with the initial conditions. Now we're going to look into the capacitor. So if we have a capacitor, V of C equal to C times I of t. Okay, in time domain it is always, we're going to use the small letters with suffix t as a time dependent quantity, Vc of t. Okay, so here I'm assuming initial condition 0. So initial condition 0. What is the voltage across the capacitor? Vc of t equal to, in time domain, 1 over c integral of it dt. Okay, or if I want IC, that, or I of t equal to c times dvc by dt, vc of t by dt. Okay, now when I convert this into S domain, here I will end up with I of I equal to, or IC is the current passing through the capacitor. IC equal to C times S times VC. Okay, so I can say VC, voltage drop across the capacitor, is IC over CS. That's in S domain. Okay, or Laplace domain, also called Laplace domain. Now if I have initial conditions, so initially assume capacitor is half charged or quarter charged. So if I take with initial conditions, so here is my C, VC, IT. Now initially, assuming that it has some initial charge or initial voltage across the capacitor, which is, I'm taking that as V naught. Okay, so with initial voltage V naught, so VC equal to, or not VC, IC equal to, sorry, so let me take this off. IC equal to CS times VC minus V naught. Sorry, I think made a mistake. So it's supposed to be something like this. S is outside, C VC minus V naught. So here I will end up with VC or IC equal to SCVC minus SV naught. So VC equal to 1 over SC IC plus V naught over S. My apology, let me redo the whole thing. So I'm assuming there is a initial voltage across the capacitor. That initial voltage is, I'm taking that as V naught. So initial voltage V naught, assuming initial voltage across the capacitor is V naught. I'm sorry, I made a mistake there, I'm redoing it. So I of t equal to C times dVc by dt, Vc of t. Okay, it's in the time domain. Okay, now when I convert this into I of s equal to c times s times v of s minus v naught. Okay, v naught is the initial voltage. I'm going to use, I mean, there are, once in S domain, we can use the capital letters. So S times Vc minus V naught, that equal to S times C Vc minus C times V naught. Okay. So V of S capital letter, Laplace transformation, it's always capital letter. Okay, V of S in S domain, or let me say, I mean, I'm using C, Vc equal to 1 over Sc times I of S. I mean, I'm taking S domain. That's the reason I'm using S, so don't get confused. So basically, sometimes I'm saying Vc, sometimes I'm saying Vs. They both are same. Vc is the voltage drop across the capacitor in S domain. Okay, that's what it is. So Vc equal to 1 over SCIS plus V naught over S. This is the voltage drop across the capacitor with initial condition. Okay, now in the next video, I'm going to talk about properties of Laplace transforms. Thank you.